everybody, Gianmarc here. Let's talk about thermodynamics. Specifically, let's talk about the first law of thermodynamics. So if you watched the music video, you might remember that the first law of thermodynamics deals with internal energy. So what is internal energy? Why don't we start with what's energy? So energy is a property that you, me, everything around us possesses, and it can never be created or destroyed, only transferred between things, and it can also change form. This is something called the conservation of energy. So maybe this sounds a little abstract, so let's talk about something a little more specific. So how about this ping pong ball? So if I have this ping pong ball here, it's an object. I said every object has energy, right? And I can transfer energy to any object that I want. So one way I could do that is, I could hold a flame up to it, right? So this is transferring energy to something using heat, and that works fine. But it's not the only way to transfer energy to something. So another example of how I could transfer energy to this ping pong ball, let's say it's on the table here, and it's sitting there motionless, and I pick it up. I apply a force over a distance, which is known as doing work. So I did work on the ball lifting it. And now that the ball is here, let's say I decide to then drop it. So I told you that I put energy into the ball when I picked it up. So it had some potential energy that I put into the ball by doing work on it. And then I released the ball, and it fell. So as it was falling, some of that potential energy turned into something called kinetic energy, or energy of motion, because the ball was in motion. But now we look at the ball and it's not moving. But I just told you that energy cannot be created or destroyed. So what happened to the energy? It has to go somewhere, right? So I said it can transfer from one thing to another, it can change forms. So what form do you think the energy is now? Would you believe me if I told you it was heat? So what happened here is, as I dropped the ball, the potential energy that I put into the ball by doing work and picking it up eventually got turned into heat. The way we could think about this is this ping pong ball is made of molecules, right? Of some polymer, some plastic. And to borrow from the famous physicist Richard Feynman, molecules jiggle. So molecules are always, they're in motion. So molecules have this jiggling motion to them that we call molecular motions. So the hotter they are, the more they're jiggling. So if something feels very hot, it's jiggling more than something that feels cool to the touch. When I dropped the ball and it bounced off the table, each time it struck the table, the impact of the table would cause the molecules to jiggle in the ball. And on the other end of that, the ball would hit the table, the molecules in the table would jiggle more. Even the air, as it fell through the air molecules would collide with the ball, and they'd get knocked out of the way, and they'd get knocked around, and the molecules would start vibrating in this sort of jiggling fashion. You can't see all of it, but what happened was that the energy that I put into this ball by lifting it eventually turned into heat. And this is a process in physics we call dissipation. So the energy dissipated, the potential energy that I put into the ball by lifting it, dissipated into heat. But maybe this sounds a little far-fetched. Maybe you don't quite believe me. Well, that's okay. You can do the experiment. All you need to do the experiment at home is a hammer and a rock. The first thing you want to do is you want to feel the hammer to see about what temperature it is. How does it feel to the touch? Then go pound on the rock for maybe 30 seconds, a minute, till you get tired, something like that. Then feel the head of the hammer again, and you'll notice that it feels hotter. And the longer you bang on the rock with the hammer, the hotter it feels. So what happens is you're doing work at the large scale, the scale that we all live on, that we call the macroscopic scale. So you do work on the macroscopic scale, pounding away on the rock with this hammer. You do work on the hammer, and energy goes into the hammer. But then when you touch the hammer with your hand, some of that energy that you put into the hammer now got transferred into your hand as heat energy. So you put energy into the hammer using work, but the energy came out of the hammer as heat. So in our example with the bouncing ball, as the ball bounced off the table, colliding with the air, colliding with the table, the energy that I put into the ball by doing work on it and lifting it off the table eventually just dissipated out into the room. If we were to talk about this ball as our isolated system, and we put energy into it, but it eventually dissipates into the room, we could say that our system is leaking energy, right? We put energy into it, it just leaks out. But what if we could define a system where we can put energy into it and it stays in there? So an everyday example of something like this would be a thermos, right? So in the morning, let's say I heat up some soup, I put it in the thermos, and I screw the lid on, and I go off to work or I go off to school, and then by lunchtime I open up the thermos and the soup is still pretty hot. So essentially the thermos is insulated, but it's not perfectly insulated, so it slowly allows heat to escape, but heat is still able to escape. But now if you were able to build a perfect thermos that let no heat escape and no heat get in, nothing, what you could do, I could heat some soup up, I could fill the thermos with it, and I could put it in a safe and write in my will that this soup has to be left alone for 1,000 years. And then 1,000 years from that day, someone can open the soup and check it out and it would still be hot. I don't think anyone would want to eat it, but it would still be hot if we could build a perfect thermos. So there's a name for something like this in thermodynamics, and we call it adiabatic. So if I can put some sort of barrier around a system that doesn't allow any energy in or out, then I've built an adiabatic barrier. So at this point, we've talked about everything you need to know in order to discuss the first law of thermodynamics. What the first law of thermodynamics essentially boils down to is that everything has an internal energy to it. And if you want to calculate this internal energy, all you need to do is add up the amount of energy that's been added as heat to the amount of energy that's been added to your system as work. So you add up all the heat in and all the work done on it. Another way that it's taught is that you add the heat in and subtract the work done by the system. Either way works. I prefer the first one. Let's put this in more physical terms. So we have some system. So let's define as our system the air inside this cylinder. So the cylinder has air in it, and that's our system. And we can add energy to it two ways. I can either do work on the system, and that made the energy go up, right? Or I can add energy to the air by just heating it, right? So either you heat it or you do work on it, and both ways will add energy to the air inside here. We can add and subtract work, and we can add and subtract heat incrementally in different ways, and in the end, the internal energy is just going to be where we ended with it, right? So let's say I add work a little bit, and then the system does a little work on my hand and pushes back, right? So I add work, then the system loses some energy. So I gained some energy, system lost energy. Or I can add energy to the system with the fire, and let's pretend that in between all of these actions, the wall around this air is adiabatic, right? So let's pretend that this doesn't leak energy, right? So then I can add some work, I can let it do some work, so some energy went in, some energy came out. And then let's say that there's some trap door here that I can open up and then let heat out and then close it again. Or I can open it up and add fire, or add some heat, and then close it up again, and then the energy will stay in there. So that's one way to think about the first law of thermodynamics. What this essentially means is that I can add energy to the system in different ways, and then the system just has more internal energy, and once it's in there, it doesn't matter how it got in there. So think back to the hammer, right? I did work banging on it, but then if you touch the hammer, it feels hot. So then energy came out of the hammer as heat. But let's try and prove this a little more thoroughly. If we have this system here that we're defining our system as the air, and I do work on it, then it has a higher internal energy at that point, right? So if I could put something flammable in there and do some work on it, then maybe I could make the flammable thing hot enough that it'll catch on fire, right? And then we'll know that the internal energy of that air must have gone up. So if we can do this, we can really prove to ourselves that doing this work has increased the internal energy, and we have evidence of this because our little cotton ball has burst into flames. Now, we've been pretending that this barrier is adiabatic, but you and I both know it is not. Think back to the thermos. When we approximate the thermos as being adiabatic, when was it a good approximation? Was it when it was 1,000 years? No, that soup would not stay hot for 1,000 years, right? But by lunchtime, it was still pretty good. So let's say you had to make a measurement that only took maybe a second to make. You could probably approximate that your thermos was adiabatic at that point. We know that it would not be exactly adiabatic, but it would be a good approximation on that short time scale. So, bearing this in mind, if I wanted to find some way of measuring energy that was put into the air by doing work on it, I'd want to do it quickly, right? So the way we can do this is we can take a little piece of cotton and we'll put it inside here, and I'll quickly push this down, doing work in a very short period of time, which will cause the internal energy of the air inside here to go up very quickly. So we know this thing leaks energy, but if I move really quickly, well then maybe I can move fast enough that that energy will get absorbed by the cotton ball and we'll see a little fireball before the energy escapes. So let's give it a shot. That was awesome. All right, so what happened here? We did some work on our system, the air, and we put so much internal energy into that some of the energy got transferred to the cotton, and it started a reaction with the oxygen that was in there we call combustion or burning. That's what happened here, and we did it fast enough that the energy could transfer before it could dissipate out of our system. So now hopefully you know a little bit about the first law of thermodynamics. Thanks a lot.